This is a brief tutorial on proportional gas laws. There's a couple other assorted topics in here. So let's talk about gases in general first. Turns out density of gases are much less than that of solids and liquids. That's because the gas molecules are very far apart compared to solids and liquids, and that's an important property of gases and the reason they behave the way that they do. Now notice there's water and there's carbon tetrachloride where densities are in grams per milliliter. You can see the water, the solid, is actually slightly less dense than the liquid water, 0.917 versus 0.998. And that's actually pretty atypical, but waters are pretty common substance. But regardless, the gas is significantly less dense. And for the carbon tetrachloride, you can still see that you have a very low density gas, more dense liquid, but you have a more dense solid, and that's more typical. But regardless, gases are very low density, meaning the molecules can move around more or less freely without much interaction with one another under most circumstances. Here's the composition of dry air. Obviously what we're leaving out is water, which is highly variable depending on the humidity, the water available to be in the air versus the temperature, and a whole lot of other complex factors. But you can see most of our atmosphere is nitrogen, 78.09%. Most of the rest of it's oxygen, 20.94%. And then that leaves you about 1%. Most of the rest of that's argon, 0.93%, with trace amounts of carbon dioxide, helium, neon, krypton, xenon, your other noble gases, trace amounts of methane produced by organic decomposition, and a teeny amount of hydrogen. There may be other trace gases that are even smaller than that. So if we're going to talk about measuring gases, we need to talk about measuring pressure. Pressure is for force per unit area. In English units, we measure that in pounds per square inch, or PSI. And in the United States, things like tire pressure is measured in PSI. But the International System of Units uses newtons as a unit of force, and square meters as a source of area, and that's a lesser force applied over a much larger area, so that pressure unit is going to be significantly smaller than PSI. But we call that newtons per square meter, a Pascal, and it's abbreviated PA. The atmosphere is measured using a barometer. 1 atmosphere of pressure is defined as the average pressure measured at sea level. So all the following are units of pressure. 76 centimeters of mercury as measured in a barometer, or in many cases it's measured in millimeters, or 760 millimeters of mercury. A millimeter of mercury is called a torr, named after Torricelli, who built the barometer and determined that the average was 760 millimeters. So that's equal to 1 atmosphere of pressure, or it can be 101.3 kilopascals or 101,300 pascals. Now in many cases people use a kilopascal over a pascal because the unit pascal is so small, unit with such a large number, and to knock 3 decimal places off of by using a kilo prefix makes the number a little bit more manageable. So you see many pressure gauges use kilopascals as opposed to pascals. And that's also equal to 14.7 psi if you want to do it in English units. So let's look at a little pressure conversion problem. This will work the same as your dimensional analysis style unit conversions from previous sections. If you're a little fuzzy on that, need a more detailed explanation, you might look back at my dimensional analysis video on my channel. So we want to convert 2.5 atmospheres to the following units: psi, millimeters of mercury, which is torr, pascals, and kilopascals. So if we have psi, we find that 2.50 atm, the conversion is 14.7 psi per atm. We see that the atms cancel, and we get 36.8 psi. Do the same thing for millimeters of mercury. 2.5 atms times 760 millimeters of mercury divided by 1 atm. atms cancel again. Gives us 1900 psi to 3 significant figures. Just that third one happens to be 0. Pascals. 2.5 atmospheres is 101,325 if you want to use that number sig figs. Sometimes people just round that off to 300. But per atm, atms cancel. You're going to get 2.53 times 10 to the 5th pascals, which is why that's not extremely commonly used. It's just too small of a unit. You get too large of a number. So what we normally do is 2.5 atms times 101.325 kilopascals per atm. atms cancel. We get 253 kilopascals, and that's a much more manageable number. So this is a barometer. If you look at this sketch, you've got a pool of mercury that's open to atmospheric pressure. The atmospheric pressure pushes on the mercury. The mercury pushes up the column where there is a vacuum. Torricelli was able to determine that height of that column is 760 millimeters, or 29.92 inches. And that's the basis of measuring barometric pressure with a mercury barometer. Let's look at some of these proportional gas laws. Boyle's law states that the pressure P and the volume V are inversely proportional. That means as one goes up, the other goes down. That assumes constant temperature and amount of gas, or moles of gas, as we'll find in gas laws. So P1V1 equals P2V2. We find that if we plot pressure and volume, pressure x-axis, volume y-axis, we get a graph in the first quadrant that looks like that, and it's pretty much a graph of 1 over x. And that's only in the first quadrant. You get a hyperbola, but we're only showing the first quadrant because pressure and volume can't be negative. You can't have less than no gas. If we plot the pressure x-axis versus 1 over the volume y-axis, we get a straight line. So you can see that they're inversely proportional. So let's look at an example. 25-degree sample helium has a volume of 400 milliliters at a pressure of 760 torr. What volume would it occupy under a pressure of 2 atms at the same temperature? So still at 25, so we can use Boyle's law because it assumes constant temperature. So we're going to convert our 2 atms because we can't have mix and match pressure units. 2 atms times 760 torr per atm. atms cancel. We got 1520 torr. We could have just as easily done the other one, but it doesn't matter. Just be consistent, and you've got to be the same in these. So P1V1 equals P2V2. So we want volume, so we're going to solve for V2. V2 is equal to P1V1 over P2. So we're going to plug everything in. 760 times 400 milliliters divided by 1520 torr. Torr is going to cancel, leave us with milliliters as a unit, and we get 200 milliliters. That makes sense. Since the pressure increased, the volume should decrease. And the pressure actually changed by a factor of 2, so the volume should change by a factor of 2 in the opposite direction. So that result makes sense. And that's the type of thing you want to do. Now we know it's Boyle's law, we can use any pressure or volume units because they're all multiplication and division. That factor is going to cancel across the proportion. We just need to be consistent in what units we use in these proportional style gas laws. Use your intuition like we did in the previous example. Decide whether it should go up or down. Some people will just take whatever the calculator spits out as being correct, and even though it's not. So think about, does the pressure go up or down? Does the volume go up or down? And did it? And that should help you decide whether what answer the calculator states is right. Charles's law. Charles's law states that the volume of a gas is directly proportional to the absolute temperature, that is temperature in Kelvin, at constant pressure and amount of gas. So we say V1 over T1 equals V2 over T2. Gas laws, you have to use the Kelvin scale to be correct, so we need to convert our Celsius temperatures to Kelvin. So the Kelvin is the Celsius plus 273. We find that the volume versus temperature graph is a straight line, indicating they're directly proportional. Think of the hot air balloon effect. You heat up the gas using the flame, the gas in the balloon is going to expand, and so that makes complete sense. So we have a sample hydrogen H2 occupies 100 milliliters at 25 degrees Celsius and 1 atm. What volume would it occupy at 50 degrees Celsius under the same pressure? So we're going to convert our temperatures. 25 plus 273 is 298 Kelvin. 50 plus 273 is 323 Kelvin. We can just use the volume unit we've got. V1 over T1 equals V2 over T2. So V2 equals V1 times T2 divided by T1. Plugging in 100 times 323 Kelvin divided by 298 Kelvin. Kelvins cancel. Leaves us with 108 milliliters. So the volume goes up just a little bit, but not a lot, because the Kelvin temperature doesn't change very much. Gay-Lussac's law, or some people just call it the pressure-temperature relationship, states that the pressure and the temperature are directly proportional. So we get a very similar equation to Charles's law. P1 over T1 equals P2 over T2. And the pressure and the temperature form a linear graph showing that they're directly proportional. The pressure of a container of helium, we'll say, is 650 torr at 25 degrees Celsius. If the container is cooled to 0 degrees Celsius, what will be the new pressure? Again, we have to calculate the temperatures. 25 plus 273 is 298. 0 plus 273 is 273. We use our P1 over T1 equals P2 over T2. And it asks for the new pressure, so we're going to solve for P2. So P2 is equal to P1 times T2 divided by T1. Plug and chug. 650 torr times 273 Kelvin divided by 298 Kelvin. Kelvins cancel. We get 595 torr. I cooled it off. So the pressure should go down, so that makes sense. Standard temperature and pressure is given the symbol STP in many cases. It's a standard reference point for many gas calculations. The standard pressure is exactly 1 atm, or 101.3 kilopascals. Temperature is 273.15 Kelvin, or 0 degrees Celsius. And those should be considered to be exact in this case. Avogadro's law states that at the same temperature and pressure, equal volumes of two gases contain the same number of moles or molecules of the gas. We set the temperature and pressure for any gas to be STP, then 1 mole of the gas has a volume called the standard molar volume. And we find that that volume is 22.4 liters at STP. So 1 mole of any ideal gas at STP occupies a volume of 22.4 liters. That's another way to measure moles, because it's much more convenient to measure the volume of a gas than the moles directly. So if I know the volume, I know the STP conditions, I know how many moles of gas are in there. For example, at STP, 11.2 liters is a half a mole, 44.8 liters is 2 moles, so on and so forth. Here, let's look at this example that's a little more complex than that. What is the volume occupied by 5.68 grams of oxygen gas, O2, at STP? So if we start with the 5.68 grams of oxygen gas, we need to get moles so we can relate it to the volume. So we're going to do a grams to moles conversion, divide by 32 grams of oxygen per 1 mole, and then use our 22.4. 1 mole of oxygen is 22.4 liters. Run that through your calculator. You're going to get 3.98 liters of oxygen gas at STP. So if you're given a mass of a gas, you need to convert it to moles before applying the 22.4 liters. Now we can combine the gas laws. If we look at Boyle's law and Charles' law, because that includes all the variables, we can look at the combined gas law equation. It's useful when all three change: the volume, the temperature, and the pressure of the gas are changing at the same time. So if we look at Boyle's law, that was P1 V1 equals P2 V2, and Charles's law, V1 over T1 equals V2 over T2. If those proportions are correct, we could say the pressure times the volume divided by the temperature is equal to some constant. So we could say P1 V1 over T1 equals P2 V2 over T2. And that still assumes the amount of gas is constant, which it usually is in most of these types of calculations. And we'll more or less work with it being constant for the purposes of this presentation. So let's look at an example. We got nitrogen gas N2 occupies 750 milliliters at 75 degrees Celsius and our pressure of 810 torr. We want to know what volume we would occupy at STP. So we have our STP conditions, T2, because these are the second conditions, 273 Kelvin, and P2 being 1 atm or 760 torr. We'll use the torr since the other temperature is given in torr. We need to convert the temperature that's given in Celsius. 75 degrees Celsius plus 273 is 348 Kelvin. Now we're ready. We got P1 V1 over T1 equals P2 V2 over T2. We want to know volume, so we can express it this way. V2 equals V1 times P1 over P2 times T2 over T1, which is just the basic algebra of solving for V2, but I collected the variables that were the same so that you could line them up and see that they canceled a little easier. So V2 then is going to be 750 milliliters times 810 torr divided by 760 torr, torrs cancel, times 273 Kelvin divided by 348 Kelvin. Just plugging in, canceling units, we'd get 627 milliliters. So we allowed all of them to change. And that's a little more difficult to predict, but you can see that the pressure went down, but the temperature went up. Or excuse me, the temperature went down as well. So there can be some competing factors there. So this has been a brief tutorial on proportional gas laws.